What's up? We are live. Wow, Meher fast in the chat. What's up, Meher, Addison, Aris, Kayla E. Oh, guys, what is up, Jose, Robles, Holler. Welcome to another episode of math class that you have to attend and watch. But you want to watch, right? Tell me in the chat, you want to be here. This is one of the most exciting parts of your Mondays. I know, Aris, you were waiting for the stream all day long. Sorry for the delay. I was sitting there at the top of my screen. There's a button on YouTube that says you're ready to go live. It has to think and process, and it was constantly spinning and spinning and spinning, and I was like, and then I realized I had to go to my software and hit a button. So I sitting there looking like this for a while, waiting for you guys, and ended up being me. So I apologize. Oh, we got some new people here finally. Here we go. Nathaniel, what's up? Aris, what is up? Oh, Aris, I already said hi to you. Kurt, what's up, brother? Addison. All right. Wow. What's up to all you people? We got 15 people here. Gershon made it. Justin made it. What's up, you guys? We are getting great close to the end. Kirby said to me the other day, she goes, "What is up with you? Why are you in so many meetings?" And I said, "Welcome to the end of the school year. Tons of meetings. I met again with Miss Douglas this morning, planning your grad and trying to get all logistics going together. I hear some of you are doing some pretty cool things at your homes. Kayla E., your mom made something. I don't know. Very excited. Make your grad as awesome as you can. Invest in it. Cole in the house. What's up, brother? So today we are in data management. Okay. And we've been in there for a couple of weeks now. Now, here's the thing. My data management probability lesson is pretty much meant to be all games. Okay? It's meant to be us in the classroom just playing game after game after game. We laugh a lot. We have a hilarious time. We go outside. We play. So I don't know how it's going to come across on a live stream. So it's not going to be as effective. But hopefully you guys understand what my mind is. And that normally I would communicate these via games. So here's what I want to do. I want to try a game. With my chat friends. Chat, you guys ready to play a game? All right, so here it is. We'll use some words that you've heard before. So Gary Sean wants to know, is this live? This is live, Gary Sean. I am reading what you're typing. Cole wants to know, how come when you search MrStav in the search bar, your channel isn't there? First off, I don't know. I think the reason why is because my YouTube channel is called Jeremy Stavropoulos and not MrStav. So if you do have tips on how I could get my Google SEO up to be MrStav, hit me with that, Cole, because I would love to do that. Yes, Kurt and Mayor are ready to play a game. All right, let's play a game. So here's the game. You're going to say stay or fold in the chat. Now, if you're watching online, live, play. If you're watching after live, obviously I won't be able to interact with you, but still play. You can still play this game because I think in my head it's going to work either way. So I am going to I'm going to roll a dice. Hopefully you can see it. Okay. And everybody who's in the game gets that many points. Okay? So if you're in the game right now, you get 4 points. Oh, put hashtag MrStav in your bio. I will do that, Maher. Good call. I like that. Okay, so everybody right now, you have 4 points. And at the end of every round, I want you to tell me how many points you have. Okay? So, chat, are you ready? You have 4 points. So what I want to ask you is, do you want to stay or do you want to fold? So if you fold, then you keep your 4 points. Okay? If you go and you stay, wait, no, stay or fold, that's the same. Stay means you stay in the game, okay? So if you stay, you go on to the next round. If you fold, you keep your 4 points. All right? So let's try this. Everybody has 4 points. I'm going to roll the dice. And we're going to add 1 point. All right? So if you're still in the game, you now have 5 points. All right? Do we understand how to play the game so far? So in the chat, you need to declare, if you're playing live, if you're staying or folding, because I don't want people declaring in the chat, I won, and people saying, no, you actually folded. So in the chat right now, say if you're staying in the game or if you're folding. Say, MrStav, I'm keeping my 5 points. All right? So just seeing everybody's answers coming in. All right? Jose staying, Maher staying, Addy staying, Cole staying. All right? You're staying in the game. You're not folding. Aris is staying. Justin is staying. Now, here's the deal. If I roll a 6, you lose all of your points. You have 0 points. All right? So, here we go. Roll again. 4 points. 4 points. Whew. Where's my whiteboard? Shout out to science. All right, here we go. So we started with 4, and then we got 1, and now we're 4. So tell me if you're staying or if you're folding. So Cole wants to know, why would we fold? So the reason why you would fold is right now you have 4, 5, 6, 7, 8, 9. You have 9 points total. Okay? If I roll a 6, you have 0 points. Okay? If I roll anything else, your score goes up. All right? Okay, here we go. I see in the chat a bunch of people are staying. I don't think anyone's folding. All right, everybody's still in the game. You guys are gambling. Roll again. Rolled a 2. We rolled a 2. That means if you want to stay or if you want to fold. If you want to stay or you want to fold. Declare it in the chat. Are you going to stay in the game? Or are you going to fold? All right. Declare it, declare it, declare it. All right. Roll again. Go. 5. Woo! Oh my goodness. We have 4, 5. That's 10. That's 14, 15, 16. You have 16 points. I'm going to change the rules for next round. You have 16 points. If I roll an even number, even equals bad. And if I roll an odd number, then you move on. All right, so Cole is folding. Cole has 16 points. Cole's locked in at 16 points. Anyone else fold? Gary Sean says, if you fold, you can stay next round. Oh, Jose says, oh no, fold. She says fold. Changes it things, eh? Addie's folding. Maher's folding. Justin's folding. Gershon is folding. Ooh, Aris is folding. Everybody's folding. Okay, well, how about this? What if instead of adding the next round, I double what I'll roll whatever I roll. So if I get a 1 or a 5, I'll double that. So you'll get 10 points added to your score. Ah, here we go. Nathaniel's staying, Kurt's staying. Oh my goodness. Here we go. Here we go. All right, so if it's an odd number, I will double it and add it to your score. All right. So if you're folded, you are safe from this round. You are safe from this roll. All right. If you're staying, you can either really, really go up or you can go severely down. Kayla Robles is staying. Kurt is staying. Nathaniel is staying. Woo, boy. Gershon staying in. Here we go. Roll the dice. If you're in the classroom, I'd have intense like music going on. 2. Oh! Oh! That's an even number. So, if you stayed, you have 0 points. If you folded, you're still at 16 points. Wow. 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 Okay. All right, so next round, everybody's still in. You're not kicked out of the game. You just have 0 points. Okay, you understand how to play? Okay, so you can either move on from with 16 points or you're at 0 points. All right, so Aris says he rolled a 5. Aris, it's not your roll that matters. It's my roll. All right, so here's the deal. So you're all in the game, and what I'm going to do is now multiply. All right, so if I go, let's do this. Okay, so let's go with this is bad. A 1 or a 4 is bad. All right, anything else? Anything else, and you move on. You add it to your point. All right? So, everybody, you're either at 0 points or you're at 16 points based on if you stay or folded. Obviously, I'm not keeping your scores. You're keeping your own scores. And if you're playing along and it's not on the live stream, keep going. Okay? So, if you get a 1 or a 4, if we roll and I get a 1 or a 4, done. Okay? So, if we look at probability here, there are 6 possible rolls, okay? And 4 of those 6 would be good, okay? 2 of those 6 would be bad. Okay, so the odds are in your favor, okay, to get a good score here. All right, and I'm going to multiply. So if you have 16 and I get a 2, 16 times 2, a big number. Okay, all right, here we go. I see the chat. Marcus is staying. Welcome, Marcus. Bonus marks for staying. All right, here we go. Roll the dice. Random.org. 6. That's a good number. Wow, that is huge. So we got to pull out our calculator because that's a lot of math. So 16 times 6. Woo! 96. I didn't really think about this. If you're at 0 points, then 0 times 6 would be 0. Gershon, that sucks. That sucks. All right, if you were at 0, then you can add 6 points. All right. All right, here we go. Let's make it a 3 or a 6. If we get a 3 or a 6, that is bad. So you still have the same odds, 4 out of 6. Okay. Woo! Yes, Mayor says, imagine if you folded. I don't think anyone folded on that round. Oh, I think Mayor folded. All right, here we go. Roll the dice. We will multiply again. Multiply here. Roll again. 4. That's good. That's good. That is good. So keep your own score. If you're at 96, it's 96 times 4. If you were at 6, then it's 6 times 4. Keep your own score. Uh-huh. All right. Now let's turn the odds. Okay. Let's change the odds here. Go back. And let's roll 2 dice. All right, so it'll roll 2 dice. That obviously didn't count. All right. If I roll a 3 or a 6, okay, that is bad. Anything else is good. Okay, Maher's at 384 points. Woo! Big man. Okay, so here's the reality. Okay? There are 4 out of 6 chances, but we have to double that, right? Because there's 2 dice. All right, so tell me, are you staying or are you folding? If either dice hits a 6 or a 3, as it just did, if either dice hits a 6 or a 3, you are busted out of the game. Well, back to 0. So, are you folding or staying? I got rolling 2 dice. Jose's out. Ooh. I don't know, Jose. I think maybe you should be in. I don't know. Well, Cole showing his math. Excellent job, Cole. Thank you, because I stopped keeping track. Addie is folding. Ooh. Oh, man. Ooh, Cole's folding. Gershon is a risk taker. Mayor's calling for a 1-in-3 shot. So what are you going to do, Mayor? Are you staying or you're folding? Mayor stays. Justin folds. Woo! The stakes are real, folks. Here we go. Let's zoom in. Let's roll the dice. If you get either a 6 or a 3. Gershon is folding now. He's retracted his message, and he's folding. Roll again. Here we go. Oh! 6. Should have folded. Should have folded. Oh, my goodness. Wow, that is devastating. That is devastating. Is anybody... we still have some people who have scores. So here's what I'm going to do. I'm going to say that if I get doubles on this next roll, anybody who's in the game wins no matter what. If I get doubles, you win no matter what. If I get doubles, you win no matter what. So stay or fold. What do you want to do? Mayor's calling for a comeback. Okay, tell me, you stay or fold? You have to have doubles. Have to have doubles. If you don't get doubles, you're back to 0. If you get doubles, game over, you win. Anybody who's in the game. Now, we can talk about odds here. We can also talk about what's at stake, right? If you're already at 0, then you might as well stay in the game, right? This is where probability comes in. Gary Shawn is folding. Jose is folding. I think Maher has nothing to lose. Addie wants to know, what happens if I don't get doubles? Back to 0. You lose all of your points. So we call this really, really bad odds, right? What are the odds of getting doubles when you roll 2 dice? Whew. So we're going to talk about, that's a good event. That's a complimentary. That's an event we want to happen, okay? Oh, Marcus is staying. Yes, so Cole wants to know if people who folded last round. So last round meant you weren't in on that round, but you kept the amount of points, and here you are in the next round. You can decide if you are going to stay or fold this round. Good question, Cole. Here we go. The game begins. I'm just waiting to see a couple more people in the chat declare their stay or fold. Let's go. Woo, I'm nervous. Who's in? Marcus is in. And I think that, and Addy is in. Addy is in. Mayor is in. Cole is out. All right. It is not doubles. Oh, devastation. Oh, Heartbreak Hotel. Oh, man. That is not nice. That is not nice. Gary Sean reports that it's a 6 out of 24 shot. Wow. Of getting doubles. We can talk about what is the percent chance there. But let's pause from this. Let's take a timeout. We can come back to it at the end of the live feed. Yeah, Jose says tough. But you have to know that anybody who was playing in that round knew that their chances were slim. And they either were just having fun and staying in, or they had nothing to lose because they were already at 0. So, every year you talk about probability, and we are focusing on theoretical and experimental. Not a hard concept at all, but Gary Sean said there was a 16.7, so a 17% shot of me rolling doubles, and I didn't do it. Okay, so make sure you have your title down, your table of contents updated. I know Kayla Robles is almost done her book. If not done, she probably is done. So gotta adapt, people. All right. So the curriculum says that you need to be able to compare theoretical and experimental probably through investigation, which is what we were doing. We were investigating. We were playing around, and if we were in the classroom, we would be playing a lot, and we would have a blast for these last couple of weeks of school. Let's not talk about that. Okay. You also need to be able to identify a complementary event and calculate its theoretical probability. Okay. We'll talk about that. So by the end of the lesson, you'll be able to identify theoretical probability. That should say experimental as well. So it's kind of redundant to say the same thing twice. So, here's a fun game we were going to play, and I'm super sad we don't get to play it. So I won't even show you it so that you don't get sad. But ultimately, we used the game to kind of make some predictions and to kind of start playing with probability. But we just did have some fun with some probability. Okay, so write this down. Probability is the likelihood or the chance that an event will occur. Now, MrStav, I already know that. That's fine. If you don't want to write it down, you don't have to write it down. Okay, this is simply me kind of just touching all my bases. Okay, don't panic, MrStav. I wasn't done writing that down. The exact same thing is right here. Okay, on the last slide. If you were trying to write it down, I just moved it up to here. Okay, so we talk about probability all the time in life. Okay, we'll say that there is a 60% chance that it's going to rain today. This one might not apply so much to you, distance learning, but I'm just kidding. There's a 95% chance that I will assign homework today. You bet you I am. Those are good odds. Those are really good odds. All right. 14 out of 30 of Mr. Stav students got an A on their first test. Is that probability? What does it look like in your life? What are some examples of probability in your life? Obviously, the big, obvious one is casino, okay, betting on sports. But look at what are things in your life. What are the chances of us getting back to school this year? Zero. 0% shot of us getting back to school at this point. Right after March break, we could have said our probability was higher. Okay, so what are the chances that we don't have school in September? That it's back to distance learning. Maybe you could argue that it's not so much zero. Maybe it's 20%, 25, 30, 40%. I don't know. We really don't know what school will look like. If we have school, will we have phys ed? I don't know. There's a lot of chances of germs being passed in phys ed, so maybe. So the nice thing about probability, it's not a yes or a no. It's what are the chances of things occurring? Okay, so there's two types of probability that we can calculate. Okay, there's theoretical and there's experimental. All right, so let's talk about theoretical. Okay, so theoretical is what we can calculate based on what we know. Okay, so the theoretical is what we know. Known information, known data. Okay, so these are calculated on possible outcomes when they're equally likely. Okay, so my example here, I'm going to make a formula. Okay, so the probability of a desired event. Okay, so depends on what I wanted. So in that case, in this game, right, if you wanted a 5, we would say probability of rolling a 5, or P bracket roll a 5. P bracket roll even number. Okay. So the probability, to calculate theoretical probability, is we take the number of desired possibilities and we divide it by the total possibilities. And we were doing that on my whiteboard. Okay, so when we said there's 4 outcomes that we would desire, and I said out of 6 options, right, I made a fraction 4 over 6, right? So there I simply was just calculating the theoretical probability of our desired event. Okay, so think about this in the chat. How would you calculate the probability of getting tails? If I flip a coin, all right, it's not landing on the edge, it's going to land on one side or the other. Tell me in the chat, what is the fraction here, or how do we calculate the theoretical probability of rolling a tails? And I'll wait for a bit to let the chat catch up. Mustard. It's about a 20-second delay here, so be patient with me as I wait. Excellent. Justin hits the chat first. Remember, you don't have to wait for other people, or you don't have to stop because other people answer. Okay. Ooh, Aris hits me with a percent. Aris reports it's a 50% shot. Kurt and Justin and Cole are saying it's a 1 out of 2. So where did Aris get this percent from? 50%. He just made it up. So here I would write the probability of flipping tails is 1, right? There's only one tail, okay, or moose head. Okay, this is the desired outcome. This is not the desired outcome. So there's one desired outcome out of 2 possible outcomes or possibilities. Okay, now, not crazy math there. Okay, where does Aris get it? Gary Sean says it in the chat. Awesome. 1 divided by 2. I need my calculator. 1 divided by 2. That doesn't make sense because Aris said 50%, and when I do 1 divided by 2, it equals 0.5. Okay, and I don't know if you guys remember earlier in the year when I was off for my surgery, you guys did this. Do you remember this? Right? Converting between equivalent forms. Right? And so here we are at a fraction, 1 over 2. Okay, when we divide the numerator by the denominator, that brings us to 0.5. Okay, that is a decimal, though. It is not a percent. And so to convert a percent, we multiply it by 100. And that's where we get our 50% chance. Okay, so the probability, excellent Kaylee, is the probability is 1 over 2, or we could say 0.5 chance, or a 0.5 shot, or a 50% chance. Okay. Now, some of you are sitting there and you're thinking, MrStav, you're going so slow. Okay. Just be patient with me. Right. I'm just trying to cover all my bases. Because I'm not in the classroom with you, I can't read who has it. Right. I often stand there and I read your facial expressions. I'm doing a lot more than just looking at you. I'm interpreting how you're understanding or not. So here I can't really grasp that. So I am going to oversimplify things at times. Okay, so we were just doing a dice roll. Okay, so the probability of getting an even number. Okay, what is the probability of getting an even number? Show me in the chat. So the question is, how many possibilities are there for evens? Okay, 2 is an even number, 4 is an even number, and 6 is an even number. Okay, the other ones are not. Okay, the other ones are not even. So I'm just watching the chat. See if you guys are going to start lighting it up. Okay, so there are 3 possible even numbers, which are good. That's the desired outcome. Now, based on what? It's based on what we put in the brackets here. Okay, this is what our desired outcome is. Okay, so if I had said a number, then things would be a little different, right? But I've declared that my desired outcome, okay, okay, is an even, so 2, 4, or 6. There are 3 possible outcomes out of 6. Okay, so there's a 3 out of 6 shot. Okay. Now Aris is again reporting that there's a 50% shot, but we just had a 50% shot with the coin. So how could there be a 50% shot of getting an even number here? All right, and I hope that I hear you talking to your computer and you're saying equivalent fractions. Okay, and so we know that 3 can divide by 3, and we know that 6 can divide by 3. And if you don't believe me, I mean, it's fair. You don't have to believe me. 6 divided by 3 equals 2, and 3 divided by 3 equals 1. As you notice, I have a chiropractic appointment. Okay, so we again have a probability of 1 out of 2. Okay, and going back to what we talked about, that is a 50% shot. 1 divided by 2 is 0.5. Turn that into a percentage by multiplying by 100, and we have a 50% shot of getting an even number. Now, again, some of you are sitting there saying, MrStav, like, boring, so easy. Okay, the idea is covering it on simpler, lower numbers that you're more familiar with. Okay, let's talk about a deck of cards. Okay, got a deck of cards. What is the probability of me pulling a heart? Okay, so the question is then, how many hearts are in a deck of cards? Okay, and we're going to exclude jokers. Okay, I'm not counting jokers. Okay, so how many hearts are in a deck of cards? Let's throw this graphic up. Okay. And so these are all the deck cards that are in a deck. Okay. And so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 hearts in a deck. Gotta go back. Gary Sean says 25%. I don't know where he got 25% from. So we'll have to come back to what Gary Sean said. All right? Cole is saying 13 out of 52 because there are 52 cards in a deck and 13 of those are hearts. Okay? So Aris is explaining in the chat what Gary Sean got 25% from. So Aris is saying that 13 times 4 is 52. So what he's saying is it's a quarter of the cards. And if we go back to my last graphic, yeah, hearts, right? There's 4 equal groupings here, right? So 13 plus 13 plus 13 plus 13 equals a deck of cards, so 52. So yeah, this is a quarter. That's 1 quarter. This is 1 quarter. Now, if you're sitting there and you're like, MrStav, I hate fractions. Okay, don't worry, we're working through it. Okay, what we're doing is we're just kind of talking the things through. This is 1, 2, 3, 4. There's 4 quarters, right? And so go back to our slide. We said there's 13 out of 52. We can always reduce, and that would bring us down to 1 quarter. And I don't know why the animation isn't playing, so we're going to go 13 divided by 13, 52 divided by 13. 13 divided by 13 equals 1. Woo. Please work. 52 divided by 13 equals 4. So that brings us to 1 over 4. Okay. Now another thing you could have done is, because 1 divided by 4 equals 0.25, so that's 25%. Now you could also go 13 divided by 52. Because they're equivalent fractions, you'll also get 0.25. And so you'll get 25% even just there. So if you're saying, MrStav, I'm not loving reducing fractions, okay, that's fine. It works even if you're not reducing fractions. Okay. You will need reducing fractions though for high school, so don't bail out on me there. Okay. All right. So theoretical probability is using known information. Okay. Let's talk about experimental probability. Let me know over the chat you're still with me. Say, yeah, I'm with you. Nothing like being alone. Okay. So experimental probability is based on data that was collected from an experiment. Okay? So the difference is theoretical, is in theory what should happen. Whereas experimental probability is what did happen. Okay? Once I completed an experiment, what was the actual probability that occurred? Okay? So make sure you write this down. The probability of the desired event. Again, whatever we want. Heads, tails, even, odd number. Okay? Picking up the 2 of clubs. Okay? So, based on data collected from an experiment. So it's number of successful outcomes divided by the total number of experiments completed. Okay? So if I got the desired outcome 3 times and I completed the experiment 3 times, then my fraction would be 3 over 3. Okay? And that would be 100% probability. Okay? If I did 100 experiments and 20 of them, okay, if 20 of them were successful, that would be a 20% probability. Okay? Just watching the chat, making sure there's no questions. Okay? So, how are they different? So think about it. Try. I'm going to wait. I'm going to give you some think time. And maybe you don't want to talk to your computer because you think that's weird. Okay? Or maybe you're happy to talk to your computer. Okay? Or maybe you want to put it in the chat. Whatever you want. But I want you to actually take some time and you think about it. How are they the same? Or how are they different? What makes them different? And if we were doing math journals, this is what I would ask you. I would ask you to explain each one, and I'd ask you, how are they different? So think about it. Take a second. Okay? So in a way, we kind of already talked about what was different between them, right? In theory, it is based on potential possibilities, and experimental is based on what actually happened. Okay, once I completed an experiment. Can you guys hear Paxton crying? He just started crying. Let me know in the chat if you can hear him crying. All right, let's look at experimental probability. Okay, calculating the probability. I spin the spinner 20 times. I got 4 blues, I got 11 purples, and I got 5 yellows. Thanks, Horace. Okay, so these are my results. Okay, I got a lot more purple than I did blue. So I would ask you, find the probability or the experimental probability of spinning a yellow. Okay? So here's where it's a little tricky, is you have to understand, what am I asking? If I was asking for theoretical probability, none of this information matters. All that matters is the spinner, right? So there's 2 yellow. So in theory, there's 2 over 1, 2, 3, 4, 5, 6. Okay? Or we could reduce that to 1/3. Okay? Or if you don't want to do it, you just go 2 divided by 6 equals times 100. So there's a 33% chance, theoretically, of spinning a yellow. However, I'm not asking for the theory, I'm asking for the experimental probability. All right, so Jose hits the chat first. Excellent job, lady. All right, so she says that there are 5 over 20. So let's look at, she says 5 over 20. Where did she get these numbers from? Okay, so the bottom, the denominator, is how many experiments were done in total. Okay, so let's change my color. Magenta, coming for ya. Here we go. Ooh, yay. So we did a total of 20 spins, and we got yellow 5 times. Okay? So there's a 5 out of 20 shot, or there was a probability. So let's say 5 divided by 20. If you're yelling at the computer, you can reduce that. You sure can. All right, so it's a 20. It was a 25% probability that it actually occurred in my experiments. Okay, so you're going to notice that the probabilities are different. The experimental probability was 25, whereas the theoretical was 33. Okay, that's kind of important for you to know. Okay. All right, so all right, so this is me just explaining. Okay, so let's look at this one. Okay, again, the theoretical probability is going to be different than the experimental probability. Now, in theory, you have the same percent chance of rolling a blue than you do a purple, than you do a yellow. Okay, so we said there's a 33% chance in theory of spinning these colors. It's an even percent shot. Oh, I don't know why it says red there. There's no red. There's no red. So that's a typo. Okay, so in theory, they have the exact same percent chance of happening, but look, blue like never got spun, and purple was quite often. So you can use this to say, maybe there's something wrong with the spinner. Maybe Mr. Stav learned a technique to ensure that he was going to get the same outcome. Let me change the numbers a bit here. There we go. Let's get rid of red. Okay. Oh, my slides are all messed up. Okay, so let's just jump ahead. I think you guys are good here. It's important that you're able to tell the difference between experimental and theoretical. Okay, theoretical. Okay, how many times did it occur? So 5, or sorry, let's do this. So 11 plus 4 is 15, plus 5 is 20. So again, I spun 20 times, and so the denominator will be 20 and whatever. So how many times did I get blue? It would be 4 over 20. How many times did it get purple? Would be 11 over 20. And how many times did I get yellow? Would be 5 over 20. Okay, so we convert all of that. So what is 4 divided by 20? That's a 20% shot of purple, of blue, sorry. And 11 divided by 20 was a 55% chance that it actually occurred. And 5 divided by 20. 25. We just did that on the last one. Okay. So these numbers are different. than their theoretical probability. In theory, they all should have had an equal % chance of happening, but that is not the reality. That is not what our experiment actually saw. Okay? As you've seen in this lesson, probabilities can be represented or expressed as a fraction, as a decimal, or as a %. Okay? And it's just a matter of switching between the terms or the equivalent forms. Okay? Let's talk about complementary events. Okay? So we did complementary events in our pregame. Okay? So complementary event is the probability of the event not happening. Okay? So theoretical is the probability of it occurring, and the complementary is the opposite. What is the chances it won't occur? Okay? And so when you were deciding whether to stay or fold, what you were simply doing was you were weighing the theoretical versus the complementary. And many of you were deciding if the complementary, the probability was too high. So if the probability of the event that you didn't want was higher, then you folded. Okay? Except for Marcus, he just stayed because he's Marcus. All right? So you've kind of always done this in your head, right? When I give you options, you always ask, well, what if it doesn't happen? Or what if we don't do it? Everly does this all the time, right? She asks me, I ask her to clean up. And she, well, what if I don't? She doesn't like the results if you don't. We talked about that for you guys. If you didn't clean the classroom, the complementary event, if you didn't, or I guess the complementary consequence was you'd be late leaving, right? So, and I would say that the probability of you not cleaning up in the classroom, it was really low because you guys were awesome and you cleaned up. Okay? So let's look at this in action. Okay? So in theory, remember the difference between theory and experimental? Experimental is based on results of an experiment. Okay? So we're talking in theory here. All right? So what are the odds of spinning a yellow? So the probability of spinning a yellow is 2. 1, 2, okay, out of 6. But the probability of that not happening, okay, so 1 out of 3. The probability of it not being yellow, the complementary event, there's 4. 1, 2, 3, 4. That was a bad idea. To write on white with white. Okay, so there's a 4 out of 6 chance. So in this case, and we can reduce that, okay, there's 2 out of 3 chances versus 1 out of 3. All right, so the chances of a complementary event happening are higher than the theoretical event, or than the theoretical probability. Okay, this, my friends, is what Las Vegas and casinos are built on. Complementary events. This is what the gambling scene, this is what betting is all, why it's a moneymaker. Okay? Because all of their games, all of their, anything they offer in a casino, it all stacks the odds for the complementary event. So people go to a casino thinking they can win money, but the odds are always higher in the casino's favor. So the casino can afford to lose some money to a couple of lucky people because the majority of people, okay, will not be so lucky. Does that make sense? Now, if you're taking notes, and I hope you are, this is important. Write this down. Okay? When you add the probability of an event with the complementary event, Okay, so when you add the probability of the desired outcome with the probability of the complementary event, those two fractions will equal 1. Oh, MrStav, we're not getting into adding and subtracting fractions, are we? Sure are. All right, so when you add the theoretical and the complementary, okay, their fraction will equal 1. Okay, now it's not just the fraction, because remember this slide, okay, it can be expressed as a decimal or a percent. So maybe some of you are like, I hate adding and subtracting fractions. Okay, we talk about both ways. Their percents will equal 100. Okay, their decimals will equal 1. Okay, so let's look at it with our example. Okay, so we said that the probability of it occurring is 1 out of 3, and the event of it not occurring is 2 out of 3. Okay, so we can put these side by side. Okay, and when we add them, remember you keep the denominator with adding and subtracting fractions. Right, so keep the denominator, and then you add the tops, the numerators. Sorry about my trackpad writing. Okay, so 3 over 3 is 1 whole. Okay. Now let's talk about what 1 over 3 is. So let's calculate what 1 divided by 3. That is 33.333333%. Okay, and let's add it with this. So what is 2 divided by 3 equals 66.66%. Obviously we're rounding, so we'll get close. So 33. Plus 66 equals 100. Okay, and that has to happen, right? Because this is covering all outcomes. So 100% of the outcomes are covered. So either it's happening or it's not happening. Okay, so the theoretical and the complementary event have to equal 100% or 1 if you're adding their decimals or their fractions. Okay. What I'm going to do is I'm going to flash this slide up here. I made reference to it earlier. Okay, and this is back when I was away when you covered this. Okay, so this is just reflecting on how to switch from a fraction to a decimal, from a decimal to a percent. I just want this on the screen so that if somebody wants to go back in time and they want to see this, then it's easier. Okay, they don't have to find it in their notes, or maybe it's in their locker. Okay. Okay, so not a lot that I actually taught. We played for quite a bit. So here is, again, we'd be playing a whole bunch and we'd be reenacting these in person. So it's kind of hard. It's less fun. Here's what your assignment was going to be. Remember I said there was a 95% chance of me assigning homework? Homework! Let me know in the chat. Who's excited for homework? Who's the most excited for homework? Okay, so here's your homework. If we were in the classroom, I always like to, try to get out of the classroom if we can, get in June, get into the hot weather. And so I always like to coordinate where we use our math class to help the primary classes. And so our project, we would skip centers. And Kurt, you're excited. I know you're excited. Cole says he's the 5%. See, your homework and your project was going to be to create a carnival game. Carnival games, like casinos, they are designed to take money. Okay? And so, in other words, there's a higher probability of a complimentary event happening. So it's higher probability that someone playing your game will lose than actually win. So it's kind of cruel, but I assign you the opportunity and I give you class time to make a game in which you have to prove to me that your theoretical probability is lower than your complementary event probability. All right? And then by playing your game, you have to prove to me that your experimental probability confirms your theoretical or your prediction that the complementary event will happen more often. And then we go and we have the little kids play it and lose playing your game. It kind of sounds bad when I say it like that, but that's okay. All right. Justin is in the 95%. He's excited for this homework. So I want to show you some games that either my students have created or that you've seen in carnivals and stuff. So here's one. You've probably seen this, and the goal is to throw a ball and get it to stay in the basket. Looks easy, sounds easy, but actually, if you just throw a ball into these baskets, it will, because of the type of material and the angle that it's on, it will bounce off and it'll come out. Okay? And the complementary event, so the ball not staying in there is far higher, and I couldn't tell you the exact percent, okay, but the actual complementary event is way higher. And so you see they spend all this money on these stuffed animals, which are really actually not very expensive for them, but people are spending more money than the actual cost of these, so they can give these away to the random people that do win. Now, if you're ever wanting to play these games, you actually have to spin the ball, land it about here, and then have it spin around, and then it'll stay in there. That beats the complementary event, the probability, theoretical probability. So, little life hack. You gotta spin the ball and allow it to rim around, and it'll stay in there. Can't just chuck it in. Okay? Here's another one, and this is very easy to calculate. Right? You throw a ball, and you gotta land it on a red. And if you get a red, you get a big prize. And if you land it on the blue, you get a massive prize, one of those ones that you carry on your shoulders, those teddy bears. Mm-hmm. Yes, Justin says carnival games are meant to be rigged. They absolutely are rigged. Okay, they're not just rigged. Okay, they are calculated mathematically for you to lose. Okay, so as you look here, it looks like a fun game. It's easy. I'll just aim. Okay, but the chances you cannot drop this wiffle ball right where you want it. Now, I did watch this guy on YouTube, and he was able to actually to hack this game where he figured out how to make it land where he wanted. Still, the complementary event was still higher for him, but he really changed the odds there. Okay, so hopefully here you can see a good, right? So here you could actually calculate how many cups. So let's say this is 10 by 10, right? So 10 cups by 10 cups. And then you could calculate, let's say so how many cups is that? 10 times 10. And so we have 100 cups. And let's say that there's only 12 blue, right? So that's a 12% chance that you will ever get a prize. right? So think of the complimentary event. It's way higher there, okay? Now here, let's say there was, go away, bug. I say there's, because the blue is the big prize, right? Let's say there was 18 red cups. So we could say that these are positive events for the person playing, right? So that's 8, 9, 10, 1, 2, 3. So we have 30% chance of getting a prize, right? But that's still a 70% chance of not getting a prize. So the complimentary event here is like not even close, right? Not even near 50-50. Okay. Now here's a carnival game. And if you hook a fish, you get a prize. Prize every time, they say. Always. Okay? But what they're saying is if you hook a fish, or if you hook a duck, you get a prize. And so this is designed so that parents actually do spend their money. Well, what prize do you get? You're going to get a dinky little toy if you get a duck. But out of 100 ducks, maybe only 2 have a prize. Like a good prize, right? So the probability here, 2% versus 80% chance of losing. Okay, but prize every time, they say. That's, sure, here's a pencil. Okay, here's something I don't care to give you. You can have it. Okay, here's some swag that has my my company name on it, so you'll give me free advertising, right? Here's one. Now a student made this, not this version, but they made one. And it's a very frustrating game. It's kind of like that wiffle ball game we saw earlier. It's really hard to play and really hard to win. It's super fun because to get these where you want them, it's very frustrating. So that was fun. Good calculations there. You see these ones you can knock over something, right? So you get 3 balls and you have to knock over something, right? So you can do the math here. Here's one, punch a hole. Right? You get 3 punches, but let's say only 2 jars actually have a prize in them. Okay, so you can play with the stats here. You can play with the math. How many punches do you get? How many things have something filled in them? Okay. So this is another version of the duck game, where you just pick it up and turn it. Okay. A lot of you love ball. Ball is life, and you always see these. Okay. Oh, I'm a baller. I hit shots anytime. Okay. So why is it that these games make money? Why there? Why are they there? Because who said it? Justin. Justin said they're rigged, right? These rims are rigged differently, right? They do not bounce like your normal rims. The thickness of these rims are modified. They're not normal, right? So you actually have to make like a perfect shot. And look at this guy's form. That is beautiful, right? So the complimentary event, even if they didn't rig it, okay, the chances of making a basketball throw or shot are actually lower than making it. It's not a 50-50 shot. Okay, your chances go up the more you practice. Okay, but this is a foreign net that you're not used to, and a foreign ball and a setup that you're not used to, and so you'll see that more people will miss the shot, and so the carnival makes more money off of these. This is often my favorite. Throw a dart, pop a balloon, get a prize. That's it. Bust 1 to win. Okay, but the actual chances of hitting a balloon, not good. All right. Now they're not bad, right? So this game is a little bit more higher chance of winning. Okay. This game is similar to the basket game. This is a student who made this. Okay, similar to that basket game where you can't just throw it in and it's going to stay there. It's angled so that the ping pong ball, you throw it in, it won't stay in. Okay? It's kind of a thing for carnival games. It has to look easy so that someone buys in. This is a super cool game. This is not student made, but I had a student make a version of this. And it was drop a ball into this fish tank, and wherever it lands, you get a prize based on its color. Ours is, are we just looking at carnival games? What I'm doing is I'm just showing you different game ideas and how you can look at the theoretical and experimental probability. Right, so here you can look at, you complete 7 experiments. How many times did you actually get a pink? Right, so if out of 7, I only got pink 1 time. Right, so carnival games will play the games, figure out the experimental probability, and then or the complementary event probability. And what they'll do is set their prices, set the chances of winning, set the $3 for 5 balls, or you only get 2 shots, or whatever. Okay, Plinko, you know this game. Drop something and it'll bounce anywhere randomly. You can calculate that. Deal or no deal. This is super fun. If we were in the classroom, I would ask somebody to make this. You see that there's 6 cars, and so you need 6 players to play this game. And everybody gets a dice to roll, and you roll your dice, and if you get a certain number, then your car can move forward. Right? So this is fun for groups of friends to play. And so if you're the carnival, you're getting 1, 2, 3, you're getting 6 payments, but only 1 person wins. So you're only giving 1 prize for every 6 people who play, right? So even there, your odds are in your favor, no matter what. Okay, and so this game was super fun. A student made it last year, and no, 3 years ago, 2 years ago, maybe 2. It was super fun. We had a lot of fun playing it. Okay, so your assignment, your homework. Don't worry about the deadline. I didn't change that. That is not an actual day. You are to design and build an actual carnival game to be played. Now, obviously, we can't play it with the younger kids out of school, so I want you to play it. I want you to show me, and I will post a flip grid, and I want you to show me you playing it. Okay, this is not designed to be stressful. This is designed to have some fun in math. Okay, so make some stuff. You can go back and look at some of my ideas. You can Google your own ideas. Okay, I will not be throwing hate on you. I just want to have fun watching what you create. Don't spend money on this. If you want, you can, but I'm not telling you to. Okay, this is designed for you to have something fun to do during quarantine. And tell your parents, I'm playing for math. Okay, so let's have some fun. Man, I have all these other games I want to play. I have another version of STAV. Oh, you guys would love STAV. We would have a blast playing that. So there you have it. Experimental, theoretical, and complementary event. Hopefully you are comfortable with all those terms by now. And that's it, folks. Peace out. Thanks for joining. Hope you are enjoying the beautiful weather, that you're getting active, that you're getting excited for grad, that you marked it on the calendar, told your family and friends, gave them the link, and all that. So, from my house to yours, have yourself a good day, and I will go back to working on boom. Aris, first one to say bye. Peace out, Aris. Later, friends. Later, Cole. Thanks for joining us live. So, Marcus, what do you think now that you know what the homework is? Jose says, do we send a pic of the game? I would love to see a quick video. You don't have to be in the video. I'd love to see a video of you playing the game. Cole wants to know, are you using OBS? Yes, sir. Yes, here's a look. So if you don't know what OBS is, OBS gives me the ability, there's my camera. my webcam. And then here's the second screen, and here's the third screen, and it might be awesome today. You can see my audio. And I can go, woo, two of me. Yes. There you go, Cole. A little behind the scenes magic. And so OBS is what sees my green screen behind me and edits it out so that I can be on top of wherever I want. All right, later, Tiana. Later, Maher. Later, Robles. Justin, Kurt. So yeah, I'll send note. Go to MrStav.ca/math, and I'll have the link for the Flipgrid. I'll have it up in the next couple of days. Okay, so Flipgrid.com/STAVmath will be it, but I'll post it on my website. Coolio. Have fun, guys. Have fun with it. And if bonus points, if you can make it easy to make so that someone could create it and play your game. But it's just all for fun here, folks. This is a fun week. There's a little relaxation this week.